Hello and welcome to the screencast for Chem Activity 44A, Overview of Carbohydrates, subtitled What Makes a Sugar? This screencast is for Allied Health Chemistry, Chemistry 120 at Missouri Southern State University, and I am Dr. Michael Garoot. This activity is a transition between the organic chemistry activities, of which there were just a few, and moving into the biological chemistry activities. So this kind of bridges the gap, gets some final organic chemistry concepts, and moves into biochemistry, where we start talking about carbohydrates, lipids, proteins, and nucleic acids. If I look at the weekly schedule, the rest of this unit, where we do carbohydrates, lipids, amino acids, proteins, enzymes, nucleic acids, that would be the biomolecules. And then the final unit, week 7, will be the metabolism unit of biochemistry. So the biological chemistry, biochemistry section is divided into the biomolecule section, which is in week 6, and the metabolism section, which is in week 7. So let's get started. Model 1, glyceraldehyde. Simple sugars have a molecular formula of CnH2ON, meaning that for N carbon atoms in the sugar, there are N oxygen atoms and 2 N hydrogen atoms. The simplest sugar, a monosaccharide, is glyceraldehyde with the molecular formula C3H6O3 and the structure shown below, which you can see here. And let's begin with critical thinking question number 1. Circle the aldehyde functional group in the structure of glyceraldehyde above. Pause the video and do this now. So this is review. The aldehyde is the group that has the carbonyl with the hydrogen attached, and it does have an alkyl group or a carbon-containing group on the other side. Question 2. What is the value for N of N for glyceraldehyde in the formula CnH2ON? Pause and write your answer here. All right, so you see how that works? What is the formula for glyceraldehyde? C3H6O3. If N in the generic formula is 3, do you see how that comes out to C3H6O3? All right, pause and write a sentence for number 3. Pause now. So do you sort of see why they're called carbohydrates? For each carbon, there are 2 hydrogens and an oxygen, so 1 water or 1 hydrate for each carbon. All right, let's move on. If we were doing this in the classroom, I would now hand out molecular model kits where black atoms, which have 4 holes in them at tetrahedral angles, are carbons. Red atoms, which have 2 holes at the same angles, are oxygens. And white atoms, which have 1 hole only, are hydrogens. So this suggests that you could make the model. If you have a model kit, you should go ahead and do this. If you don't have a model kit, I have made molecular models for you on some computer software called ChemSketch, which, by the way, if you wanted to, you could get a copy of ChemSketch. You go to a website called ACD Labs, and you can download a free copy of ChemSketch for yourself. So if I look at these 2 models, and I'm going to compare that with this. So the question I have for you, I'll move this around a little bit, is which of those structures is matched by this model? You can rewind the video if you like and look at this more than once. So I'll point out that this central carbon has an OH and an H. This carbon at the top has one oxygen and one hydrogen, so that's your aldehyde carbon. I've put it at the top. And this carbon at the bottom has two hydrogens, an O and an H. Notice how I have this middle carbon arranged so that the carbon at the top and the carbon at the bottom are going backwards away from you, which you can tell when I rotate it to the side, right, that they're now rotated to the back. So the question is, I want you to now circle which of the two structures on this page does it match. Pause now and make your circle. Okay, so did you pick this one? Remember, the wedge at the left and the wedge at the right mean those atoms are coming forwards out of the page or off the screen. The dashy lines here and here mean that those are going backwards away from the viewer or behind the page. So that is in this orientation. Here's my OH on the left, my H on the right, and those are pointing outwards towards the viewer. So that's this one. Number 5 says make a second model of glyceraldehyde so you have one of each. Well, we can't make a second one because we couldn't make the first one, but I can show you the structure of the second one. So pause. So shortly this one will just turn right into the other one. And there it is. Now I have the other structure. And you see how in this one the OH group on the middle carbon is over to the right hand side. I still have my carbon at the top that has only one O and one H, so that's the aldehyde carbon, and at the bottom two hydrogens and an OH. So that is the other structure. And the question is, can you rotate or twist them so that the atoms are in the same place in both molecules? So as I'm doing this, as I rotate it around, is there any way that it's putting this OH group on the left side and making it look like the other structure? And it's difficult for me to get it into that orientation. This is the best I can do, the OH on the left and the H on the right, but notice that the H pointing to the left and the OH to the right are not any longer coming towards the viewer. See how they are actually pointed away from the viewer. So if you have these in models in your hand, it might be easier to see, but the answer is no, you cannot make this one into the other one. You have to, if you had the model kits, you would have to actually physically pull this oxygen off, pull this hydrogen off, switch their places, stick them back together, and then you could do it. So the answer is no. So what we've discovered there is there's a new kind of isomer that we haven't seen before. The kinds of isomers we'd seen before, remember, were the most similar, or of course identical, but then you had conformers when you can rotate them around single bonds and you have the same structure. These are not conformers because you can't rotate them around. These are not cis and trans isomers because what would they be cis or trans to? I can't find anything. So it's a new kind of isomer. And this particular kind of isomer is called an enantiomer. So that's how you pronounce that word. It's five syllables, enantiomer. And here's a definition for you. A pair of non-identical molecules that are mirror images of each other. Oh, so we're going to investigate how these molecules can be thought of as being mirror images of each other. And it turns out that whenever you have one carbon that is bonded to four dissimilar groups, you could say four different groups, four unique groups. Whenever that's the case, you will have this capacity. such that when you switch those two of the groups, you get something that is not the same as before you switch them. And then you'll have a pair of enantiomers. This particular carbon that has those 4 dissimilar groups, and this one, is then said to have a handedness or a chirality. Chirality is a Greek word based on the Greek root word. It means handed. So just like people have left hands and right hands, which are mirror images of each other, these molecules can be thought of as being left-handed and right-handed and being mirror images of each other. So number 6 says, just confirm that the center carbon of either glyceraldehyde in question 4, which are these, is connected to 4 different groups. The key thing here is groups. It doesn't mean 4 different atoms. So this carbon in the center is connected to an H on the right, an O on the left, a carbon on the top, and a carbon on the bottom. If you were just saying atoms, you'd say, oh, well, carbon on the top and carbon on the bottom is the same. But that's not how we think about it. We think about the entirety of the groups. So it's an OH group, an H group, a CH2OH group, and an aldehyde group. So is everything in this circle the same as everything in this circle? Clearly not. So that's 4 dissimilar or 4 unique groups. Got it? And I sort of already talked about this. Are these geometric isomers or enantiomers? Explain that in a complete sentence. So I sort of talked around it. I guess now would be the time for you to pause the video and see if you can write that in a sentence. So pick your answer, write a sentence, pause now. This is probably the easiest sentence you can write. They are mirror images of each other. If you're not seeing that they're mirror images of each other, just be patient and we'll investigate that here as we go through the next model. So let's do that now. Model 3, L and D glyceraldehyde. So to distinguish the 2 isomers, chemists call the one on the left L-glyceraldehyde and the one on the right D-glyceraldehyde. This is just a little trick that you can use to help yourself remember which is the L and which is the D. You have to draw it like it has shown with the aldehyde carbon at the top, and then when you draw a line down through the 3 carbons and then draw the D to go through the oxygen in the middle, that makes a D, and so that's the D isomer. If you tried to do that on the wrong one, you would draw your line this way and you would go through the oxygen and you get a backwards D, and that's nothing, right? So D. So that makes this one the L and this one the D. All right. These are different ways that you can draw the structures. We've been looking at the wedge and dash. This is a new way. It's called the Fischer projection. This Fischer was, well, he was a biochemist that was looking at sugars, and this is the simplest sugar, and he just got tired of drawing dashes and wedges all the time. At least that's how I imagine it. And so he just decided to draw as a cross and make a convention. And the convention would be that every time the lines are going horizontally, that they mean wedges, and every time they're going vertically, they mean dashes. And so you just have to translate that. So when you see it written this way, you can just translate that yourself. Oh, everything that's horizontally has to be a wedge, and everything that's vertically has to be a dash. And then you get the same thing that you had before. Okay? So question 8 here says, this Fischer projection, which I claim is L-glyceraldehyde, does not exactly match the one in figure 1, which is this one. So look at them, explain how they're different and why both of them are correct. Pause now and write an answer. Okay, so it says explain how they're different. I actually did that second. all that happened is a rotation of the aldehyde group into a different conformation. Here's the aldehyde group. And if you imagine rotating around this single bond so that the hydrogen rotates towards the back, the oxygen rotates toward the front, and then you keep on going so that the oxygen rotates over to the left and the hydrogen on the right, then you get it into this conformation. And that's just a single bond, so you're allowed to rotate around there. That doesn't change the position of the OH on the center carbon, which is still on the left side, so it's still L. And that's how I've written it. Let me take a minute to compare. Okay, I was able to get these both up at the same time. So if I'm looking at this molecule, this is the D molecule. This one is the L molecule. And it's fine to rotate around. You could just spin around this carbon. You're going to spin around this carbon. This O would move over here, but that doesn't change the fact that the OH is still on the right side, so it's still D. And even if I spin around this, that OH is still on the left side, so that's still L. Here's some information. Because you have one chiral carbon, one chiral center, you can use those terms interchangeably. There are two enantiomers, right-handed and left-handed, L and D. Interestingly, L comes from the Greek for levo, which means left, and D comes from the Greek for dextro, which means right. And that's what L and D mean in this context. So if you have two chiral centers, then you have 4 options. Every time you add another chiral center, you multiply the number of options of what we call stereoisomers by 2. This just says 16 possible isomers. I'm saying that those are called stereoisomers, which we actually talked about. Let's see. Right, the title of Model 2 says types of stereoisomers. And so depending on how many chiral carbons there are, each time you have another one, you multiply by 2. So if you have 4 chiral carbons, then you would have 2 to the 4th, which is 16 possible stereoisomers. And you always draw them, well, you don't always, but the standard way of drawing them is to put that aldehyde, the most oxidized carbon, at the top, and then you look then at the very last or the bottom chiral carbon to determine whether it's L or D. So let's apply that. Before we apply it, we need to also define 2 more things. An aldose, meaning a sugar containing an aldehyde, and a ketose, meaning a sugar containing a ketone. That's pretty simple. And then you can mix terms together. So if they're 5, they're a pentose. If they're 4, they're a tetrose. If they're 6, they're a hexose, etc. So let's apply those terms. And let's label each of these carbons. Let's get that to go away. Let's label each of these simple sugars, monosaccharides they're called, with one of the terms in this list. Okay, so just write them right underneath. Pause the video and do that now. Glucose is an aldohexose. Galactose is also an aldohexose, right? Next. Fructose is a ketohexose. This is a ketone, carbons on both sides of the carbonyl group. Well, L-fructose obviously has to be a ketohexose also. And do the final one. All right, did you get that one? Great. Let's move on to number 10. circle each chiral carbon. Hint, there are a total of 17. So you'll have 17 circles. So pause now and see if your 17 match mine. Go. So there they are. For each and every one of those circles, I can look at the groups that are attached to it, and there should be 4 different groups. So let me just pick one at random and explain it. So let's pick at random this one right here. This carbon number 3. So let me erase these other ones for the time being. So if I'm looking at that carbon, then the 4 groups that I'm considering are the hydrogen, the OH, then everything at the top and everything at the bottom. And is everything at the top the same as everything at the bottom? No, they're different, so that's why that's a chiral carbon or a chiral center. See how that works? Great. Consider the 2 isomers of fructose in figure 2. What is the difference between the L and D isomer of a simple sugar? So take a look at those and write what is the difference. Pause now. So I say they're mirror images. Do you see it? You imagine a mirror right here. And at each chiral center, you're seeing the opposite there. So if this one is looking at that one in the mirror, it sees the reverse at each of those chiral centers. And since these ones aren't chiral, it doesn't matter what they look like. But the ones that are chiral, you see the reverse. This chirality thing, handedness thing, you can look this up on Wikipedia, and it talks about examples of chirality, like this example where, and this is for chemistry, where it shows a carbon with 4 unique groups as being a handed kind of thing. But that doesn't just show up in chemistry. It shows up in real life too, as if chemistry is not real life, right? Of course, we're all based on chemistry, which is based on physics, and biology is based on chemistry. Something that is handed is like a seashell, for example. You can have a left-handed version or a right-handed version. They talk about the dextral, there's the right-handed thing. They have the sinistral, which is the left-handed. We're mixing our Greek and our Latin there. I'll talk about those root words at another time. Well, no, I'll just mention it now. Sinistral is the Latin for left-handed, but sinistral sounds like sinister, which sounds like evil, right? Because back in the, let's say, the Dark Ages, left-handed things were thought to be evil and right-handed things were thought to be holy. And this is also why right is a synonym for correct. So if you're left-handed, I didn't make the language, I'm just teaching it. So I apologize for the language. We know better than that now. We know that right-handed and left-handed have nothing to do with whether something is holy or evil. All right. So maybe it's easier for me to show this example instead of with a snail with a screw, because I found this picture. So if you have a screw, it has a certain handedness. You probably have a way to remember that: righty-tighty, lefty-loosey, right? If you turn it to the right, it's going to tighten. If you turn it to the left, it's going to loosen. But if you make a mirror image of a right-handed screw, it's a left-handed screw. It would actually turn the opposite direction. The way that I would talk about that is a screw is chiral. To be chiral is to have the property of handedness. So one thing can be chiral or exhibit chirality, but in order to have enantiomers, you have to have 2 of them because they come in pairs, the right and left-handed version. Something that is achiral, A means the lack of, so it's not chiral, like a nail, because if you make the mirror image of a nail, it's just exactly the same. I try not to use the word achiral because if I'm pronouncing that out loud, if I say achiral, am I saying this is a chiral thing, or am I saying this is an achiral thing? That's too confusing. So I just don't use that terminology. And finally, this image shows you specifically why chirality is referred to as a handedness, because you're not going to be able to see all of that, are you? So let's just look at it this way. When the left hands and the right hands cross over each other, they don't match up, but something like a bottle, when you make the mirror image of that, then it is the same as itself. Okay, so let's go back to our activity. Well, let me just mention, I think it said this, but I didn't say it out loud. The sugars that exist in biology are nearly always the D sugars. So these sugars, D-glucose, D-galactose, D-fructose, D-ribose, those are all found in biology. L-fructose, almost never found. There's not a good explanation for why that is. It just is the way, the best, you could just say that's the way the universe was made. All right, so now that's the end of that particular unit talking about chirality and enantiomers. We need to talk about one other thing with regards to sugars, and that's how do they cyclize and how do you connect them together? Because you have simple sugars, monosaccharides, but in biology, these monosaccharides end up being connected together into disaccharides, polysaccharides, right? Di means two. You can have oligosaccharides, which means many. You can have, or which means several, right? Like di would be two. Oligo would be several. Poly means many. What's the cutoff between several and many? That varies. Maybe several is 3 to 7. Maybe it's 3 to 20. Maybe many is 20 plus. It's a gray area. But in order to connect them together, they're going to cyclize. So here's the information. The simple 5 and 6 carbon sugars often react with themselves to make cyclic structures. When this happens, it makes a new functional group called a hemiacetal. A hemiacetal has both an alcohol and an ether group attached to the same carbon. So here's an example. D-glucose, just copied down exactly the same as it was right up here. I've numbered the carbons for you. And now this is also D-glucose, but if you had the model, you could see you just bend it around so that carbon number 1 is right here, and you bend it around into a circle. Carbon 2, 3, 4, 5, and then 6 up here at the top. And what happens is the OH group from carbon number 5 makes a bond to the carbonyl group on carbon number 1. And when it does that, this double bond goes away and picks up an H to make this OH group. And this O ends up with 2 bonds. So the hemiacetal carbon is right here because it has an OH group and an O with a carbon. So there's your OR group attached to the same carbon. That's the hemiacetal. I am going to ask you to be able to, from memory, draw both the straight or open chain version of D-glucose. This is the most common simple sugar. You really should know the structure of glucose. So I'm going to ask you to be able to draw that from scratch in both the open chain and the cyclic form. So here's a hint for how you make that work out. When you draw the cyclic form, It's always a 6-membered ring with an oxygen in it. And then, once you've learned to draw the straight chain, remember it's an aldehyde at the top. There's 4 chiral carbons, each has an OH, and then a CH2OH at the bottom. And the OHs go right, left, right, right. Right, left, right, right. So that's just a way to remember how to draw the structure of glucose. And then when I follow my carbons around, if they were on the right, they go down. So this is number 2, so it goes down. Left is up. Right is down again. And then right. So you actually have to remember that that one is already drawn because it's sort of down compared to the up. And the up is going to be carbon 6, which is a CH2OH. The down is that O, which was that OH, which was that OH, which is already drawn. So right, left, right, right becomes down, up, down, down. And then you actually have 2 choices for where you put this new OH group. You can put it down, which is alpha, or you can put it up, which would be in the beta position. So this is alpha D glucose, but what I've drawn over here is beta D glucose. The difference between alpha and beta is where you put that OH group on carbon number 1. If you put it down, that's considered alpha. If you put it up, that's considered beta. I'd call this the alpha anomer because this is the anomeric carbon. I call this the beta anomer. Alpha and beta are different stereoisomers because I've made a new stereoisomer because I have a new chiral center. And it really makes a difference. When you hook alpha glucoses together, you make starch. When you hook beta glucoses together, you make cellulose. And they're completely different molecules. Starch, you probably have some. You probably have in your cabinet some cornstarch. You can take that and put it in your soup or your gravy to make it thicker. You can digest it. You can eat it. It's fine. Cellulose, you make paper out of it. If you try to eat that, you're not going to get any energy out of it. It makes plant cell walls. So even though they're both made of glucose, completely different properties. When you connect one sugar to the next, you now have what's called a glycoside or a glycosidic bond. So when I've connected one sugar to the next, which one is the glycosidic bond? Is it this one or this one? So technically, you can't really tell the difference. So you can just say that the glycosidic bond is that connection between the two. The glycosidic bond over here is the connection between the two. And so what you need to be able to do with this is to look at 2 sugars, figure out if they're alpha or beta, and figure out which carbons are connected. So if I've made 2 glucoses, how do I know these are both glucose? There's 6 carbons. The OH is down, up, and down. 6 carbons, down, up, and down, which is right there. Those are both glucoses. And if I number them, I've connected carbon 1 on the first sugar to carbon 4 on the second sugar. And on carbon 1, this oxygen is pointing down. We said that was alpha, so that's how I describe this glycosidic bond. Alpha 1, 4, or sometimes you see it alpha 1 with an arrow to 4. You see it both ways, 1, 4, or 1 joined to 4 with an arrow like that. This is maltose, also known as malt sugar. You might be familiar with it. If you get some malt sugar and you put it in your milkshake, it becomes a malt and it has that flavor. Or if you heard of malted milk balls, then you know what the flavor of malt sugar is. Malt sugar is made by breaking down plant starches, and you might have heard of it also in reference to malt liquor, which is what you get when you ferment malt sugar. You make malt liquor or beer is made in the same way. Over here we have another disaccharide, which is lactose. Lactose joins not two glucoses, but one glucose and one galactose. So if I look at these, I can figure out which one is which, just like I did before. 6 carbons, but the OH here is down, up, and down, so that's glucose. 6 carbons, but the OH is down, up, and oh, look at that, it's up. The only difference between glucose and galactose is that one chiral center switched at carbon number 4. And when I look in the straight chain, remember I see the same thing. The only difference is 1, 2, 3, 4. The OH is on the left. So see glucose, right, left, right, right for the OHs, and in galactose, right, left, left, right. We just changed one OH that made it a completely different sugar. So this one on the left is the galactose, this one on the right is the glucose, and now we can use this alpha and beta terminology. We look at carbon 1, the O is on the top, so that's beta, and that's joined to carbon 4 of the second sugar, so beta 1 to 4. So if these are food molecules, in order to digest these, an organism needs to have an enzyme that can break these glycosidic bonds. It's the same for polymers of alpha or beta glucose. You have enzymes called alpha glycosidases and beta glycosidases. There's an enzyme that breaks this down. It's called lactase. If you are lactose intolerant, then you have a deficiency of lactase. Okay? You should be able to recognize these disaccharides. You should be able to, given any random disaccharide, you should be able to tell what kind of linkage it is. Is it alpha or beta, and which carbons are connected? So you could do this kind of nomenclature for the glycosidic bond. So let's sum up and make sure that you are understanding what this is. So considering these figures, 3, which was this guy, which we spent quite a bit of time on, and 4, which is this one, explain what is meant by alpha and 1 and 4. Pause the video and write a sentence. Pause now. Okay, I wrote 2 sentences. Alpha means the OH on the anomeric carbon, C1. That's not chlorine, that's C1. C1 is down, so that O is down, but it's not OH in this case, so I guess we would just say O. Let's erase that. The O on the anomeric carbon is down. And 1, 4 means that C1 of the first sugar connects to C4 of the second via a glycosidic bond. So that's what a glycosidic bond is when you connect the anomeric carbon to an OH group on another sugar. I didn't mention what kind of reaction that is, but that if you think about it, you had an OH on each of those, and you've lost some of that. So if I did have an OH, just imagine I had an OH here and I had an OH here. And now I only have an O. What's missing? Well, I've lost 2 H's and an O, right? So that's losing water, so that's a condensation. If I were to try to break these back down, I would have to break the glycosidic bond, add an H back to here, and add an OH back to here. And that would be a hydrolysis, adding water to split the disaccharide into 2 monosaccharides. All right, let's, by analogy to number 12, let's go ahead and do number 16 and, number 13 and number 14. So just go ahead and do both number 13 and number 14. Pause now. So I'm not going to read those to you, but you can pause the video and look at what I have and compare with what you have. I'm relatively confident that you got this. So you're on to the exercises. So in the exercises, it talks about the difference in monosaccharides, so describing those. Labeling figures based on which sugars they came from, which I actually talked about. And number 3, where you're going to have to do some reading on your own. So find descriptions in your textbook. If you don't have the textbook, or if you'd rather, you can just use the internet and just Google them and find some descriptions of these polysaccharides: amylose, amylopectin, and cellulose. Describe the similarities and differences among those 3 polymers. And that's something that you'll be responsible for knowing on the quiz. Even though I'm not talking about it here, you need to do a little bit of homework on that. And there's plenty of space on that page to do that. Okay? We're to the end of the screencast for activity 44A. And we're about to the end of my voice. You can probably tell that I'm getting a little scratchy. So I think I'm going to have to take a break from recording the screencasts, but I will get back to it just as soon as my voice allows. Cheers!